So as we get the object closer, see right now we're at 11 centimeters 10. As we bring it back up, we get an increase in centimeters. So I'm going to bring it way up here, way down here. It's pretty responsive. Surprisingly not that noisy. But then again, the resolution isn't that high because I have not enabled for decimal values in the UART, but we'll get there. So coming up is a tutorial on how to get this to work from scratch using bare bones embedded systems in C programming. Hello everyone, welcome to my video. Today we're going to be talking about microcontrollers. We're going to be writing drivers. Specifically, we have this ultrasonic distance measurement sensor that we will be writing a low-level driver in C for this microcontroller right here, which is a TIVA C microcontroller, TM4C123G series, ARM Cortex-M architecture. And so we will be configuring the microcontroller's peripherals. Specifically, we're going to be working with timers, and these timers have different modes, and one of the modes that we're going to be using is input edge detection. I will talk more into detail as to why the case, but the higher level understanding is that we're going to be measuring the duration of certain events, because that's how we will convert that value into a distance. And so this video is intended for embedded engineers in training that are, starting off. I myself still consider myself in that category. More than anything, this is just as an exercise to see what type of problem-solving skills an embedded engineer needs to have, and to be able to work from scratch with the data sheet and with just low-level C, and as well as being comfortable with bitwise operations. So enough talk, and let's get to business. Okay, so before we delve into the data sheet, first and foremost, I would like to talk a little bit about the physical intuition behind this. So how we can derive from first principle physics what we would actually need to measure in order to get a distance measurement. And so let's get this underway. So this is our sensor, right? So please bear with me. I understand this is very elegant artistry. And this is the sound module right here. And so this is sort of like a side view. This is our x-axis, and out of the screen is the y-axis. And so this is the object that we're trying to measure the distance of. And what this module does is it sends out a burst of sound waves like this. They're actually, I think, ultrasonic, I believe. And then it bounces off the object, and then it reflects back. And this is a delta x distance away, correct? And then, so then we know from physics that the delta x is equal to, so the distance of the object, so I should actually add a 2, because it's the total distance, which is how to get there and then how to get back, is equal to the time that it took to travel multiplied by the velocity of the speed of sound. And we can actually solve for, well, how far away is the object, right? It's simply this equation. And it's pretty simple. If you were to tell me, if we were to do this experiment, suppose we could actually do this, and we're in some sort of big alley, and you have a stopwatch, and you're like, hey Max, like screen something, and I'll be able to hear it because I have like really good hearing, and I'll time it and I'll tell you how long it took. And because we know the speed of sound, which is v, we can actually know how far the alley is without actually even having to measure it. Just suppose for a second that's plausible, because this is pretty much the analogous situation. So pretty much, if you know the time of, I'm reiterating just to make sure we understand this, if you know the time that it takes for the sound wave to go forward and backward, then we know the distance. That's simple. So it would be great if we could actually know how long that object how long the sound waves took to get to that object and come back. Well, guess what? This sound wave, this distance measurement transducer does exactly that. It actually returns a signal. So it actually returns a signal into its echo pin, and this is going to be plot. So this is voltage, this is time, and this is echo pin output. We will see exactly where the echo pin, but it's pretty much one of these pins right here, echo pin, and the output will be this pulse signal with a certain duration, delta t. And this delta t is exactly what I just mentioned. It's how long the sound wave took to travel forward to the object and then bounce back. And then, so if we could actually figure out a way of measuring this, right? The pulse width, which is defined by the signal enclosed by the rising and falling edge, if we can measure this with the microcontroller by doing peripherals, then we're pretty much set. And then we can know the distance, and we repeat this indefinitely. However, we have to be able to know how to trigger this measurement, and that's what I will talk about next.
Okay, so we're going to talk exactly how we're going to use the microcontrollers in order to generate in order to generate a trigger signal. And what we need to do is we need to generate a signal that looks like this. So it goes high, and then it's maintained high for a duration of 10 microseconds. And again, this is according to the data sheet. So this is trigger signal. And well, how do we do this? The first thing we need to do right here is we need to, so in order to define the signal, we have to set a voltage up to high. So we're going to do that by using one of the general purpose input-output ports, specifically one of the pins. And then, so at 1, so the first thing we need to do is enable set pin to high, a pin to a high voltage. So I'm going to do like a pseudo code sort of. So GPIO port D data, and then we're going to set the specific pin that you want to use, pin high. And like I said, we have to maintain this for 10 microseconds. Well, how do we know that those 10 microseconds have expired? So think about what's happening. We have a microcontroller, and it's running at a certain frequency, so each instruction takes a small tick of time. And after a certain amount of ticks of time, 10 microseconds will have passed. Well, that's when timers come in. So we're going to enable, as soon as we enable this on, we're going to want to enable the timer. A timer that goes off onto an interrupt service routine after 10 microseconds. Well, what needs to happen after those 10 microseconds? So when we're in that when the processor takes us to that interrupt service routine, which we'll call it timer handler, what exactly needs to happen? Yep, you guessed correctly. We have to toggle that pin. We toggle the pin that we had just set earlier. And that'll allow us to accomplish this. And then what do? Well, at that point, the ultrasound module is going to be able to output to us an echo signal. So in order to be able to measure the pulse width of the echo signal, we then enable timers for timing the pulse width of echo signal. And this is accomplished using input capture. So we're going to use the timers and the pins to look for the input and to use for edge detection. So we're going to use the rising edge of the signal and the falling edge of the signal. And this needs to be timed, so that's why we're going to be using timers. And we're going to also be using interrupts in order to measure the difference between these two times that's going to be recorded within the timer counter registers. So I should add that we actually are going to be using an extra timer in addition to the two sets of timers which we have. We have one timer that's responsible for generating this trigger signal here, and then we have another set of timers actually, so in total there's 3 for the edge detection, one for each edge. So one timer will go off after this edge. We will have a register that tells us the time of the processor at which that happened, and then we save that in memory, and then we have another interrupt for the downwards edge, and then we have the time in the processor at which this happened. We take the difference in those times and we have our pulse width, and so this is where the timer comes in. So first, I'm going to present what we could do. We could just use only one timer for we will generate the trigger signal, right? So what we could do is after this we set the pin high again, and then we sustain that for 10 microseconds again, and we utilize the same one-shot timer in order to tell us when 10 microseconds have passed, so that at that same interrupt service routine we would then repeat the same process of, okay, we're going to set that pin to low again, and then we're going to get ready for edge detection again, right? And then we're going to repeat that process indefinitely. However, what I'm going to do is we're going to add a buffer period here. So this green means buffer. So at the end of this interrupt service routine, so rather than enabling it again, this trigger signal, we're going to use a timer here that'll go off after some delta T buffer. And after that goes on, then we hit another interrupt service routine. So this is the same exact logic applies to this timer. So then we enable the one-shot timer to go off after 10 microseconds again. And then this red will, and then after some time we get ready to take the measurement. So that's what we're going to do. So I should add on to here. We're going to use a buffer timer that is enabled right after we finish measuring the pulse width. In the interrupt service routine of the edge detection timer. And well, what are we going to do? So this is going to be buffer. Let's write some pseudocode for what we do. Buffer timer handler. So then we enable the timer to go. So after the time has expired, we go to the handler. The handler is then responsible for enabling pin high again, so that we're triggering, and then we enable the previous timer to go off after 10 microseconds. And then what's going to happen when that goes off? We're back at this initial ISR that I talked about. And then after this is just an infinite loop. This keeps happening until how many ever measurements you want.